Forgot to crack that. Okay. Aww, someone's trying to scam me on my texts. All right, so let's take a look at this pattern. What are we thinking here? Yeah. What's happening in this pattern? What's changing as this moves? There's more blocks. What? How many blocks were added going from figure 1 to figure 2? They added how many extra cubes? They added 5 cubes. How many cubes did they add to get from here to there? They added 5 more cubes. So what kind of equation is this going to be? If we wanted to write an equation for it. Linear. If we are adding the same amount straight off the bat, that's going to be a line of in some way. And in fact, this will be our slope. So if I wanted to write an equation for this, I know it would start with something like 5n. How could I figure out what my mx plus b thing would be? What would be my plus b?
Yeah, plus 1 because it starts at.
I was going to say, only thing is starts at would be 0. So 1 is 1. 2 goes with the total here. So something we can do, if it's not something we spot where we could figure out what figure 0 would be, because that's technically where our y-intercept would be, I could use the fact that figure number 1 has 1 block. We know that we usually write these as a y equals mx plus b. We know our 1 and 1. So if 1 equals 5 plus b, what's our b going to be? Because negative 4. Because this was my 5 times 1. So negative 4 equals b. So writing our equation, we could have our y equals 5x minus 4. That x being our figure number, because we had figure 1 that had 1 block. So if we want to know what happens on figure 21, what could I do? Plug it in. And what do we get? How many blocks would it take for figure number 21? 101. There are other ways through things, like the way that I show you guys, like that yesterday's with the triangle thing, this one with the finding our linear equation. Not the only option. There are a gabillion ways through these. I'm just showing you one that it's kind of a common way through. Again, not the only way through. If you wound up with this answer, what you did was probably fine. We just want to be able to try and get it so that even if I ask you 21 or 57 or 132, we're not having to sit here and add 132 times. I don't want to have to do that. That's a lot. Okay, so it's all about trying to find the pieces in the pattern that change and how they move. Okay, Kai? Questions on that one? Because then we are going to go in our books and we're going to look at some stories. We're going to start looking at some quadratic equations because our chapter is all about quadratics. And I'm going to I put it up at the very, very end of yesterday. This is the same thing that was up on the screen yesterday, but I'm going to talk through them. I want you to write down all 3 of our forms, and I would highly recommend that we write down the little tidbits next to it. Page 73 has some blank space at the bottom of that graph. We're not going to be using that graph, so you can write underneath it. We're not going to use it. Yeah. This space down here would be a good place to put these. We want our 3 equations. So our standard form, which is the one that has no parentheses, That's our y equals ax squared plus bx plus c. A, B, and C are called the coefficients. And the important piece that's on our standard form that we can find with no math needed is we can find our y-intercept. Is C. It is C. So we can write it as an ordered pair, 0, comma, C for our y-intercept. That guy. Then we have our factored form next. That's this guy here, where we have that A equals x minus R1 minus R2. Sometimes we'll see it that way. Sometimes we'll see it with R and S. Sometimes we'll have it with P and Q. Doesn't really matter what the letters are. It's going to be any kind of variable there, or any term. And all it is these two pieces, the R1 and the R2, or the R and the S, or the P and the Q, whatever the pieces are, those are our intercepts. Our roots, solutions, zeros, those guys. So these pieces are the roots. So I can write them as R1, 0, R2, 0. It's our x-intercepts. So again, no math necessarily needed to find these pieces. It's just whatever number would be subtracted from x here. And the last form we have is our vertex form, which tells us the vertex. And that's our y equals a parentheses x minus h, close parentheses, squared, and then plus k. And we have our vertex. Is it h comma k? So it straight up tells us where the vertex is. And what we're going to be looking at today is we're going to be looking at a lot of like stories and situations and trying to write equations or compare equations and looking at our values here. So we're going to look at a couple of them, and we're going to build some equations, and we're going to do a little bit of stuff. So we are actually going to start on the next page. We're going to look at page 74. I'll leave this up here for a second. And it's using, they've got a story here talking about how the standard form for a quadratic is used in projectile motion, aka gummy bear flight. And this particular situation, they give us an equation. There's a couple of weird things in what they're talking about at the top of 74 that I want us to talk through, simply because there's a couple of weird notations and they've made one error in the equations that they give us. So, does anybody need more time on this page? Okay. So, this is what's at the top of the page on page 74. The meters equation has an error. So, I would recommend fixing that. Cross out the minus 9.8 in the 4 meters and put a minus 4.8. They forgot to divide it by 2. We do not need to like memorize them or anything. These things look really, really, really weird because of these little baby numbers that they've got. Like this guy. They talk about this guy a lot. This is what they call the initial velocity. The way we say this, if it has a little baby number 0 at the bottom, this would be V naught, N-A-U-G-H-T, meaning 0. It really is not something we're going to see super often, but when it pops up, it makes things look so much ickier. Like it really does. All that means is speed at launch. I was going to say, however fast it goes. So like if I had my catapult, it would be speed. however fast I launch it. Honestly, it's not going to be something we calculate very frequently, but it looks at these equations, and anything that has that little baby 0, we just say it's not, and that just means at the start, they're just getting extra with their notation. It's not going to be something we need, but it's just something that looks really crazy, and so I wanted to give us the name for it. So what we're really looking at here is that these equations are our gravity equations with a couple of variables. So this is going to tell us about our height. This is how gravity applies. This is the speed at launch, and this is the height at launch. So it's our y-intercept, it's our starting position, it's where we start. So this is height, that's a G, at launch, or at the start, and this guy is speed. At start or at launch. Everything else are pieces we know how to deal with. So let's look at this specific situation here. We've got a piece of paper and a hammer that are being dropped. They're both being dropped from a still position, meaning I'm not throwing them, so there's no speed at launch. I'm just let go. Let gravity let go. That's no speed. If I threw it, then we'd have a speed. So if I'm just gonna let go, our speed is 0. And, important sentence here, we're ignoring air resistance. So basically we're doing it in a vacuum. What could I do to write an equation for the paper? What do we know about our paper in this situation? This piece doesn't have any variables we need to pick something on, so I'm going to bring it over. Our minus 16t squared. You guys got a question? Chance? We doing all right? Awesome. Let me know if you have got a question. Let me know. All right. If we're looking at this second piece here, what did they say our initial velocity is, our v naught? 0. So we're going to have plus our 0t. And then what is our height at launch? What's our height at the starting time? 90, because they say our school is 90 feet high. Can I simplify this equation a little bit? What can I do? Yeah, the 0t is not actually doing us any good. So the equation for my paper should fall at some form of 16t squared plus 90. Let's do the same thing for our hammer and see what's going on here. So hammer. Dropping it off the school at the same time. What's going on? What are we going to have? Minus 16t squared. I am still dropping it, not throwing it. So what's going to happen to my middle term? 0. And what's its height at the start, at launch? 90. So what do we notice about these two equations? They're 100% exactly the same. Does that make sense for paper and a hammer to have the exact same equation and falling like that? What do you think? Those equations are exactly the same. Why? Say loud.
Gravity's the same.
Because gravity's the same. I'm not going to do it with a piece of paper because the air resistance gets a little funky. But, got an eraser. Hang on. I'm just going to make it so we don't break the floor. Do you think this is true? Is that real or are they making this up for a math problem? You think making it up for a math problem? So yeah, not counting air resistance. So they're rounding it a little bit. I have a hammer, right? I'm not using a piece of paper because this is how I get around the air resistance thing. Do we agree that these are different, pretty different objects?
Yeah.
Do you think these are going to fall at the same rate?
Good. If that was
Good. Let's look. What do you think? What do you think's going to happen? Which one's going to hit first? What do you think? You think the hammer's going to hit first? Yeah, where you can see the rug. You think they're going to hit at the same time? Oh, I'm holding them so that the bottoms are kind of lined up. You think the hammer's going to hit first? Get where you can see. You want to watch? Ready? 3, 2, 1. Huh? Exact same time. Exact same time. And that's because with objects this small, the air resistance isn't a huge impact on it. I just have to move the rug over here so I don't like bend the floor with these. I don't get in trouble. Okay, so this is a thing that's true, and if we had bigger objects, the air resistance would be a factor. That's why I didn't use the paper, is it's so light, the air resistance will make it do the feather floaty thing. But this is actually pretty darn close to true. Yes, they round, but if I was to do this experiment off of like one of the big buildings downtown, we would start to see a difference because of the air resistance. But on stuff this small from this height, not that big a difference. So let's see what's different if we look at something that does have an initial velocity. So let's look at number 2 on this page. We've got a potato fired from a spud gun. We're not recreating this one. That is, the spud gun's at a height of 3 meters, and we have initial velocity of 25 meters per second. We are asked to write the equation for this and see if we can figure out how high it goes. So, what do we notice here? It's in meters. That's a great thing to notice. So we were given 2 equations up at the top, one of which had an error and we fixed, one of which was for feet. So our meters is the one that had the error in it when they wrote it, because there's a typo and it takes them years to fix typos. So we're going to look at our meters equation. That was that h of t equals r minus 4.9 t squared plus our v naught t plus h naught. So what pieces do we know? What did they tell us about? The height is 3 meters. Which piece does that tell me? The h. That's our h naught. That's how high the little stand is for our little potato launcher. What else do we know? Our initial velocity of our 25 meters per second. Which piece of our equation is that? It's our v naught. It's this guy. So we can fill in these pieces and get that our height, based off of time, is our minus 4.9 t squared plus 25 t plus 3. Filling in the pieces. The question they ask us is, how high does the potato go and when does it get there? What are we looking for when we ask how high does it go? It's maximum, also known as its what's the other word for maximum? Starts with a V. Vertex. Can we find the vertex in this form of the equation right now? With things that we have talked about so far? No. So if I really wanted to know how high this is going to go and when is it going to get there, how could I find that out? I was going to say, we could go graph it. Like, we could go onto Desmos and graph the dang old thing. So, let's go take a look at it. I was going to pull it up for us. Come on. Exit. There we go. And on Desmos, what we can do is we can type in, jerk complexities down that. There we go. R minus 4.8. It won't let us do t very much, so we're going to switch it to being x squared. Then we had our plus, what was it, 24 t, but again, we're switching our t's out for x's. And then we went plus 3. And we can get our whole graph here. I'm going to change a couple of settings just so it looks better on the screen, making everybody a little bit bold. So we can get our graph up here. About how high do you think this thing goes? And what time does it get there? 2.5 seconds. So even if we don't have the capability right now to find that point, we'll get there. We can use tools at our disposal. We can use technology to get there. Desmos is available on an app, or on your phone, or on your phone book. But we can type it in, and you can click on it, and you can read points that way. So we can find how high it's going to go. But that's not something we can do just from the equation at this point. So what we're going to do next is we're actually going to skip page 75 and 76 and 77 for right now. Wait. No, 77 is where we're at. We're going to skip 75 and 76 for a minute. I think we're working with those tomorrow. But I want us to look at number 5 on page 77. It's the very top one. And what's happening here is we're going to give you some information. And we're going to use this information to try and model an equation. We're trying to write an equation for a parabola. So if I give you points -3, 0, and 6, 0, and 4, -5. So I've got 3 points here. What do we notice about these points? What do we notice about these points? More specifically, what do we notice about these points? They're both on our x-axis, meaning these are our x-intercepts, which also means that these are our roots. So what we can do is we can actually use this information to write an equation in factored form. Because our factored form equation, that was our y equals whatever our a is, x minus r1, x minus r2. So what are our roots up here? What's our root for this one? It's our first root. -3. What's our second root? 6. So we'll have R2 be 6. So I can fill in those couple of pieces right there. Whoa, wrong pen. Y equals a x minus -3. What happens when I have x minus -3? Turns into a plus. So we get +3. And x minus 6. Awesome. It's a great start to an equation. But there's too many variables left. I've got x, y, and a. We've got to figure out one other thing. Somehow it's going to involve this last point. What can I do with that thing? It's an ordered pair. It's an x and a y. If that's on my parabola, it should make that statement true. So I can then use it to solve for a. So I can substitute in that last point my -5 and for the y. And then we have our a, substituting in our x, which is that 4. So 4 plus 3. And 4 minus 6. Now is there stuff I can do and simplify? Because we've got our -5 equals a times 4 plus 3 gives us 7. 4 minus 6 gives us -2. So what is 7 times -2? A times -14 gives us -5. So how do I get a by itself? Divide by -14, and it's incredibly unpleasant. What is -5 divided by -14? Does it simplify? Yeah, I was going to say, you could put it as a decimal. We could also leave it as a fraction. Is it going to be positive or negative? Positive, because I had a negative over a negative. So this tells me my a value. That means I can come over here, I can finish in my equation, and we can be done with it. So we'll have our y equals whatever our a is. We just found our a to be 5 over 14. Then we have our x plus 3 and our x minus 6. And that is our equation for this. So if we're given 2 roots and another point, we can write an equation. We have to have 2 roots and another point to be able to figure out that a value. We can do it sometimes with just 1 point, but only if we have one very, very, very specific point. Because we can take our 2 roots and make a factored form. We already have done it where we have taken our initial starting speed and made a standard form, so I wonder what form we're going to talk about next. Oh my gosh, what? Let's go one more. One more like this. Let's use that last one. Okay. So then we have a very similar problem. It's the one right below it. We're given the vertex of a parabola is 15, -30. And that our y-intercept is going to happen at 0, 25. What can we do with this? Vertex form. They straight up tell us this is the vertex. If we have the vertex, use vertex form. That one was our y equals a x minus h as a quantity squared plus k. On my vertex, it's h comma k. It's always in alphabetical order. X then y, h then k. They're in alphabetical order when they get into ordered pairs. There's something on the edge of my stylus. So when I go to substitute those pieces in, we have our y equals a x minus our h, So we're x minus 15 squared plus k plus negative 30. Do I need to have both the plus and the negative there? No. Is it okay to have both of them there? Totally fine. It's not the best math grammar, but it's not wrong. So now I have our equation kind of half filled in. But we have too many variables still. I have a y, an a, and an x left. I got to figure out what one of the things is. Just like we did on the last one, we're given another point. I have an x, y point. So now I can substitute those in for x and y. I can use that to solve for a. So I can take and substitute in my 25 in for the y. What's up? And we have that equals our a times our x, which was 0, minus 15 squared minus 30. What should we do? Say it louder. Yeah, let's simplify a little bit. So we've got our 25 equals a times negative 15 squared minus 30. Because we just took our 0 minus 15. What should we do next? We want to find what a is. I want to get an a equals. You guys got an idea? Because you're sure having a nice conversation back there. I'm going to assume it's on topic with this. So what should we do next, guys? I want to get my a by itself. I was like, I actually kind of want to leave the a where it is. Say it a little louder, Cameron. I can't hear you. Yeah, we can do our exponent. So we can do our 25 equals a times 15 squared is 225 minus 30. Still looking to get my a by itself. Add the 30 to both sides. So plus 30 plus 30. That's going to give me 55 equals a times 225. Yeah, divide both sides by 225. That's going to leave my a by itself, and we can use our calculator to help us figure out what this fraction is going to be because it's kind of messy. What is our a going to equal? I don't know the decimal off the top of my head. You can write it as a fraction, or we can put 2.4 repeating. When we have a repeating, it makes it really kind of icky to do into an equation. If it's a non-repeating, totally fine. But if it's a repeating one, I do recommend we keep it as a fraction, which was 11 over 45. Which, if you are in the yellow calculator and you get a decimal and you'd rather have a fraction, if you click the button that has the two triangles, like, that's a bad triangle, like this, it'll switch your decimal into a fraction, or your fraction into a decimal. So if you hit this button, it'll put it into a fraction or a decimal. Okay, so our a should have been 11 over 45, somewhere around there. So our whole equation here, I'm going to grab this one. We have our y equals our a, which was 11 over 45, x minus our 15, that was squared, minus 30. So we can take some points and we can use them to figure out how to write these equations. We don't have to know equations to be able to write equations. We can take pieces that we find, be it points we're given, intercepts, roots, vertexes, whatever. We can use them to create equations. So sometimes we'll be given information in a story, sometimes we'll just be given points. Okay? So the one that we skipped over that was the page 75, I encourage you to take a look at, but honestly it's more important that we went through these two than we spent time on that one. That's why I jumped it, and we were only going to come back if we had time, but we only have about 5 minutes left. And I like to try and not talk us all the way to the end, because I know how it is, and I know we are seniors, and I know we are kind of exhausted mentally with it, and I get that. So we got like a 5-minute brain break before we have to go to 7th period. Okay? So our chapter test is going to be right before spring break. That is the Wednesday before spring break. And this one, it is a test. Okay? So it's kind of the vibe. That's where we are right now. All right? You guys will have an e-learning assignment for Thursday because that's SAT day and you guys won't be here. Tomorrow we're going to do a different, like a activity. But Thursday we will have an e-learning assignment. Excuse me, dear.